Okay, so let me just remind you that this is about proving a well-posedness result for the Einstein equation for rough data, and that we have, for this well-posedness result, we had to prove what are called bilinear estimates and also null forced Rickards estimates on a rough background. And the main tool, basic tool that we needed was a plane wave representation that I rewrote here that I presented yesterday. So this afternoon we'll talk about, actually the topic here is to talk about how you control, how you make sense, how you actually first construct this plane wave representation. So again, I'll come about this I'll come back on this this afternoon. That's a construction step. That's about generating any initial data for the wave equation, and then how to control this representation formula, which boils down to controlling the so-called error term. Okay, so this will be the topic of this afternoon. But this morning, I'd like to discuss even a more basic building block, which is the control of the econal equation. Okay, so the parametric, the plane wave parametrics is a Fourier integral operator with a phase u. So let me forget for now about the u plus minus because I will treat each of the half wave in the same way. So I have the main building block of my plane wave representation is this solution of the econal equation, and I'd like to discuss how you control it, because obviously the better I control it, the better I control my Fourier integral operator. So the better I control my plane wave representation. Okay, so here this morning I'll be solely interested in how to control the so-called econal equation. Okay, so let me remind you that the econal equation. So you have a scalar function u that goes. So actually u, in principle, it goes from m, from the space-time m. I have a space-time m. So remember, I have a space-time mg. The dimension of m is 4, and g is the Lorentzian metric. So g has signature minus plus plus plus. And on this space-time, the only thing I'm assuming is that the curvature tensor is in L2. So I have curvature tensor in L2. And I'd like to control, actually, let me be more specific. It's actually, because you propagate the initial data, you actually propagate the information that it's L infinity in time, L2 in sigma t, if sigma t is my foliation by a time function. Okay, so I have my sigma naught, which is my initial slice, where curvature is in L2, and I'm propagating this information. So this is my, if you want, my bootstrap assumption here. And now I'd like to control this econal equation where, well, u depends on tx. So tx are not coordinates. I mean, it's just to say that I'm on the space-time. And then you also have a parameter omega, where omega belongs to S2, and tx belongs to the space-time. So in other words, u is a function from your space-time cross S2 to R. Okay? And again, you should see, so m here, omega here, respect, this equation is a purely space-time equation. So it's an equation on the space-time. So here, omega is simply a parameter. Okay, and you should think in terms of Fourier parameter too. It's a parameter in the phase space, not in physical space. Okay. Okay, so I'd like to control this by. Okay. Sorry. Just put this down. Okay. So you have this equation, and the only thing you assume again is curvature in L2. So you see, of course, it's an equation based on your. I mean, it's on your space-time, and it explicitly depends on the metric. So obviously, because the metric has only curvature in L2, this is going to severely limit the regularity. Okay, so the question is, how much regularity can you get for this equation? And here, let me first, I'm going first to introduce some basic objects which are going to allow us to control this equation. So first, let me introduce the space-time gradient of my function. So the covariant space-time gradient is, as usual, defined by this. So L is minus G alpha beta d alpha u d beta. I mean, it's in a coordinate system, but it's in a invariant object. It's the gradient, the covariant gradient of u. And then, because you satisfy the econal equation, it's very easy to see, it's a straightforward computation to see that if I take the dot product of the gradient with itself, if I do GLL, I get 0, which means that L is a null vector. And furthermore, if you look at the level surfaces of U, you know that the normal to level hypersurfaces of U is precisely the gradient of U. So that means that the normal to these hypersurfaces is null, and therefore these hypersurfaces are null. Okay, so the level hypersurfaces of U are null hypersurfaces. Okay, I'd like to make another remark, which is that again another straightforward computation using the fact that you satisfy the equal equation yields the fact that DLL is 0, so that L is geodesic. Okay, in particular, because it's null geodesic. Okay, so in particular, so what do you have? You have that if I start with a geodesic, right? If I so first of all, so if I look at the geodesic, if I look at the curve gamma naught is L gamma, because L is geodesic, then because I have DLL is 0, that implies that again gamma is geodesic, and because GLL is 0, that means that gamma is a null geodesic. Okay, so gamma is a null geodesic. And also, if you look at U evaluated at gamma, if I look at U evaluated at gamma dot, that's G of du gamma dot. But because du is L and gamma dot is L, this is GLL, and therefore this is 0. Okay, which means that U is constant along gamma. Okay, so this should remind you of something. I'm constructing curves where explicitly U is constant along these curves. So this is simply the method of characteristics. Okay, so and indeed, if you look at this equation, this is nothing but a nonlinear transport equation. So I could have said from the beginning that I can just use the method of characteristic to solve it. But of course, the interesting thing here is that the characteristics are clearly identified as null geodesics of my spacetime. Okay. Okay. So for now, it's just a remark. This is certainly not the way we're going to. I mean, we're not going to use the method of characteristics to control this equation because we want to do something much more refined since we're in a very rough setting. But it's good to remember. I mean, it's going to be useful later to remember that somehow. You could solve it by the method of characteristics in a smoother space-time. I mean, it's important to remember this fact. Let's say. Okay, so now, again, this is not the way we intend to control it. So let me introduce some objects which will allow us to control the equal equation. So I'd like first, again, to introduce these level hypersurfaces of U, HU. So it's just the point in space-time of constant U. Okay, so again, for now, I see omega as a parameter. So I'll talk about the omega dependence later, but for now, you could think of omega being frozen. For now, it doesn't matter too much. It's only later that's going to matter. L, again, is my space-time gradient, and I'd like to, since it's the generator of null geodesics, I'd like to define the affine parameter, which parameterizes my null geodesics. So, okay, so you have your null hypersurfaces, which is spanned by null geodesics. Okay, so if I look at H, so that's HU, that's my level hypersurface of U, which is a null hypersurface. And now I look at the null geodesic spanning H. So now I know that HU is spanned by null geodesics. So it's just a congruence. H is just a congruence of null geodesics of direction L. And now I'd like to, all of them, they have an affine parameter. I could say that, for instance, the initial hypersurface, so if this is sigma naught, I could set S to be 0 on sigma naught arbitrarily. And then I just parameterize each of my null geodesic by an affine parameter such that L of S is 1. And then I can identify the points of constant S along this null geodesic. So that gives me a two-surface PSU of constant S and constant U. Okay. Okay. So it's just I'm just building a foliation of my null hypersurface. Okay. So I want to foliate my null hypersurface by these constant S surfaces, which gives me these two surfaces PSU. Okay. So maybe let me redraw it. So you have this HU. That's HU, my hypersurface of constant U, and then HU is foliated by these PSU surfaces. And here you can So L again is the normal to HU. It's actually also the normal to PSU simply because all vectors in HU are orthogonal to L, so in particular the one on PSU. So inside HU, L is the normal to PSU. And yeah, and let me remind you that we have built a frame. So now I'm going to reintroduce this null frame. So you have this E1, E2, which are normal to L, and which are going to be an ortho. So I'm going to take for E1, E2 this direction which are normal to L and which complete the frame. I'm going to build them such that they are in the tangent space of PSU. Okay, so E1, E2 span, it's an orthonormal basis of the tangent space of PSU. And then you have this last vector L bar, which completes the null frame. And remember that you had these relations such that, so GLL, L is null, so GLL is 0. L bar is null, so L bar is null, is 0. And then GL bar L is normalized to be -2. And then you get, in particular, and L bar and L are all orthogonal to E1, E2. Okay, so these are all the relations of the null frames that we established last time. So I have this null frame, which is now adapted to these two surfaces PSU. And let me just tell you what you get in the flat space. Yeah, it's important to have in mind this picture. So in the flat space, you're in the Minkowski spacetime. Remember the analogous in the flat space, the solution of the equal equation, which depends on omega, is t plus x dot omega. So it's minus or plus, but let me just treat one sign. So it's t plus x dot omega. The hypersurfaces, the level hypersurfaces of U are now hyperplanes. T plus x dot omega is equal to U. So in other words, you are foliating your spacetime with hyperplanes that are all parallel to each other. Let me draw a picture here. So you have, in other words, in the flat case, so if you look in R1 plus 3M, you have this foliation of your spacetime by hyperplane that are all parallel to each other and are all orthogonal to the same direction. So let's say 1 omega, right? 1 minus omega, sorry. They are all parallel to each other and orthogonal to that direction. Okay, and L is dt minus omega gradient x. L bar is dt plus omega gradient x. And finally, PSU are simply planes of constant t at constant x dot omega. Okay, so that's the situation. And now let me introduce the so-called connection. So I can now introduce the connection coefficient of my null frame. Okay, so in other words, to control the solution of the equal equation, I'm simply going to differentiate my null frame because in particular it contains the gradient of U, and I'm going to control all these connection coefficients. So these connection coefficients, they live at the level of two derivatives of U. So here essentially, I'm controlling U by controlling its Hessian. Okay, so I'm controlling all the possible components of the Hessian of U. Okay. So here, so there are lots of them. Actually, I think I have to define in principle. I would have to define, I think 9 components. But I'm going to stick to simply 2 of them because it's these are the ones that I'll use for the explanation. Okay, so let me just simply give you a very restricted set of components of the Hessian of U, which will be this. So the first one. I can, in particular, take the dot product DAL. So, sorry, yeah, okay. Forgot to put that notation. Okay, so, yeah, it's probably not great. So, okay, so E4, sorry, I thought I removed that, but if you see an E4, it's L, and E3 is L bar. It's just because it's easier to note it that way, but probably, okay. So anyways, so this is the second fundamental form of PSU because remember the normal to PSU is L. So I'm differentiating L along directions which are tangential to PSU. So that's exactly the second fundamental form, right? I mean, maybe there might be a sign convention, but let's forget about this. This is, in essence, the second fundamental form of your two surfaces PSU. And this corresponds this would correspond to the Hessian of u in the direction of PSU. Okay, so it's the Hessian of u in the direction you want it to. Again, remember my convention, when I have a capital A, capital B, it means index is from 1 to 2, so it means E1, E2. So here you differentiate in direction of E1, E2, which is the direction of the tangent directions to PSU. Okay, so that's the second fundamental form. And I'm going also to define theta, which is the torsion, which is 1/2 of dA L L bar. So that's 1/2 of dA L L bar. And furthermore, I'd like to decompose. So this one would correspond to the Hessian of u. So you see that's the gradient of u. So that's the Hessian of u in direction of one direction is tangent to PSU, the other one is L bar. Okay, so I'll just introduce these two connection coefficients. It's enough for explaining the ideas. And then I'd like to decompose the second fundamental form. So second fundamental form, as usual, is symmetric. And in particular, I'd like to decompose. It's a symmetric two matrix because, right, it's a 2x2 symmetric matrix because you're in dimension 2 here for your planes PSU. And I'd like to decompose my symmetric matrix in the trace part and the traceless part. Okay, so I take the trace of my matrix. So when you take the trace of the second order form, as usual, you get what is called the mean curvature. So trace chi here is the mean curvature of my two surfaces PSU. And then I can define the traceless part, which is I decompose my matrix in a trace and a traceless part. So you have chi hat AB is chi AB minus 1/2 trace chi GAB. So you see that if you take the trace, this is going to cancel this, and you'll get 0. Okay, so it's the traceless part of my symmetry, of my second fundamental form. Okay. Okay, I guess that's for the notation. That's it. Yeah, let me just mention. Yeah, I just want to mention that in my error term, in what I call the error term of the representation formula, in particular, we had a term which I claimed you could have a geometric interpretation. So this term, derivation G of u, which comes up in the error term of my parametrics, and which we'll see this afternoon, it does have a geometric interpretation. It's just the mean curvature. It's equal to trace chi. Okay, so it's a straightforward computation, but it's important to remember it. Okay. 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 So now I need also to do something else, which is that what I'm going to differentiate my econal equation, and whenever I differentiate it, in particular, I'm going to commute derivatives, and I'm going to introduce a curvature tensor, which will be evaluated on my null frame. Okay. So I just want to decompose my curvature tensor on the null frame. So you take your curvature tensor and you introduce these possible contraction of the curvature tensor with a null frame. So let me quickly write them down. So you have alpha, for instance, alpha AB. So that will be a two tensor, and it's R. You contract twice with L, and the other one with E1 and EA and EB. In other words, all possibilities of E1 and E2. So you have RL, EA, L, EB. Beta is when you contract with L, L bar L, and the last one with EA, so you get a 1 form on PSU. And rho is a scalar, it's just 1/4 of R, L bar L, L bar L. So, there's a hierarchy here where I contract more. So I start with many contractions, as many as possible contractions with L, and then I start putting more and more L bar in my hierarchy until I arrive to alpha bar where I get only L bar and no L at all. Okay? So here I have as many L's as L bar for rho and sigma. So you can actually have a formal definition of signature where you would count the number of L and L bar. So here I would say that this has signature 2 because I have 2 L's and no L bar. And each time I have an L bar, each L is +1 and this -1, so that would have signature 1 because it's 2 minus 1. This would have signature 0, the rho and the sigma. And then beta bar signature -1 and -2. Okay, so you just have to count the number of L bar, and I'll say right away why this is important. This hierarchy. Okay, so this rho again, it's a scalar. It's 1/4 of R, L bar L, L bar L. Sigma is the same where you replace the curvature tensor by its Hodge dual. Yeah, well, let me not. It's not important here, so let me not specify what this is. And then again, beta bar you have 2 L bars 1 L, and alpha bar you have 2 L bar and no L. Okay. Okay, so first of all, notice that you have all the components of curvature in principle. Okay? Remember that curvature, due to its large number of symmetries, has only 20 degrees of freedom. And remember that which is equals to 0 specifies 10 degrees of freedom. So you have 10 degrees of freedom left. So as long as I have 10 quantities here, which seem to be independent, that should be fine. So you can count that here you have 2 scalars, so that's 2. One form gives you 2 and 2, so here you have 2, 1, 1, so that's 6 degrees of freedom. No, sorry, I don't know. Yeah, that's 6 degrees of freedom. And here you can actually check that this is a symmetric 2 tensor in dimension 2, so it has only 2 degrees of freedom, right? So this one has 2 and this one has 2, so if you do all together, you get indeed 10 degrees of freedom, okay? So that's the right number of degrees of freedom, and you can, indeed, that means that if you try to do other components, so for instance, you could try to come up with other linear, other contraction of the curvature tensor, I claim that they will always be decomposed back to these ones, okay? Okay, so now I'd like to mention in this setting, how do I use my bootstrap assumption that the curvature is bounded in L2? And here, I don't want to use, so I said earlier that my bootstrap assumption is curvature tensor is L infinity in T, L2 in sigma T. But this is not the way I want to use it, simply because this is not adapted to what I'm doing now. Now I'm not decomposing in a time foliation, I'm decomposing in this U foliation. So I'd like something adapted to this U foliation. So in other words, I'd like to go from an information on a space-like hypersurface, my sigma T here. Okay, so sigma T, that's my sigma T. I'd like to go from an information along space-like hypersurfaces to information along null hypersurfaces. And this should remind you of something we did in the first lecture, which I called characteristic energy estimate. Okay, so that's actually why. One of the reasons I introduced this, it's to explain how you can go from space-like to null hypersurfaces. So in other words, remember in the characteristic energy estimate, you can look at the derivatives of your wave equation along space-like or along null. And here I'd like to do the same, but with the curvature tensor. So to get energy estimate for the wave equation, you need what we have seen, which is the energy momentum tensor. So I need an equivalent of the energy momentum tensor for the curvature. And it turns out that there is such an equivalent. It's called the Bell-Robinson tensor. Maybe let me put it here. So in other words, I want a divergence relation that I'm going to integrate, and I'm going to get information either on space-like if I integrate between two space-like slices, or along space-like and null if I integrate along a region where I also put null boundaries. Okay, so this, well, let me not specify exactly how it looks like, but you can build a so-called Bell-Robinson tensor. I'm still going to denote Q like the energy momentum tensor because it's very similar, but it's for curvature. So it's a 4 tensor this time, alpha, beta, gamma, delta. So let me not specify exactly its form. It's a contraction of R with itself plus a contraction of the Hodge dual of R with itself. But let me not. I just want it's a quadratic expression in R, exactly like the energy momentum tensor is a quadratic expression in the derivative of the wave equation phi. Okay, solution of the wave equation. So it plays the same role. It's a quadratic expression, and it is divergence free. Okay, this is exactly what you ask from an energy momentum tensor. It is symmetric, so it's symmetric with respect to each index. It's quadratic, and it's divergence free. So far so good. And there is one last thing you ask for a nice energy momentum tensor. It's to have some positivity properties when you contract it with d by dt. Okay, and this is here. This is again the case. If I build P alpha, which is this Bell-Robinson tensor contracted 3 times with t this time. And this time I have 4 tensor, I have to contract 3 times to get a 1 form. And when I compute d alpha p, so what do you get when you control d alpha p? When you get d alpha p alpha, so you get so now I want to look at the divergence of this 1 form. Well, it's exactly as for the wave equation. Either it falls on Q and I get 0, or it falls on T and you get the deformation tensor. And because there are 3 here, you get 3 times the same term because it's symmetric. So you get 3 times Q alpha beta T, and then deformation tensor of T alpha beta. Okay, sorry, I need to contract, so let me put alpha beta up here. Okay, so it's the exact analogous of the wave equation. You just have 3 indices to contract with t, so therefore you get a 3 here, but that's the only difference, okay? And now I can integrate this relation exactly as we did for the wave equation. And, yeah, well, let me rewrite this. So if you integrate, obviously, again, you get a boundary term, so you get q nu ttt on the boundary of R. That's why, because you use Stokes' theorem, and then on the right-hand side, you just see on the spacetime region the term involving the deformation tensor. So 3 q alpha beta tt, and the contracted with the deformation tensor of t. Okay, so the term which is interesting. So let me, okay, let me assume that I know how to control the right-hand side. Okay, so obviously there is some work for the right-hand side, but I claim that this is this is part of the trilinear estimates I mentioned yesterday. That when you have to control the energy estimate, you have to control the trilinear estimate. This is, for this one, you are able to actually control the trilinear estimate. So let me just assume that I know how to control the right-hand side, and let me see what information I extract from the left-hand side. Okay, so from the left-hand side, okay, so let me erase this. Yeah. Okay, so in other words, from the left-hand side, either, so if you look at if dr is sigma t, for instance, I mean, if sigma t belongs to dr, then you control q t t t t t, and that would control all curvature component. That would control curvature square. I mean, all component of the curvature. Okay, so exactly as for the wave equation, if you take space light, you control everybody. And exactly as for the wave equation for the characteristic estimate, if you take null, you miss some people, simply because here, if you look at a piece of null hypersurface, so let me call this null hypersurface HU, then you don't control everybody, because now you contract, the unit normal now is L, so you get a different contraction of the Bell-Robinson tensor. And here, you only control, so that's R, you control the curvature square on L2 of sigma t. So that's how you get your L infinity L2 of sigma t. But here, you control, along the null hypersurfaces, you control what is the so-called curvature flux. So you have to contract R one time with L. So this is it's a schematic notation, which is, I mean, it's not a great notation, but it's just to say that I contract at least once with L. Okay, and then you control here, again, you control L2 along the hypersurface, but exactly as for the characteristic energy estimate, you don't get everybody. So for the wave equation, you only got tangential derivatives. So here, I only get contraction at least once with L. So you can see that in this curvature component, the only time I contract, the only time I don't contract with L is the alpha bar. All the other ones, they have at least one L, so they are fine. But the alpha bar doesn't have any L, so that's the bad component. It doesn't appear in the curvature flux. Okay, so here, in particular, you obtain that alpha, beta, that they are all L infinity with respect to U, L2 with respect to HU, except alpha bar. Okay, and that will be all. So in other words, the U enemy here is essentially alpha bar. Okay, so now let me tell you how you're going to proceed to control your econal equation. So basically, I'm going to derive what are called the null structure equation for your connection coefficients. That is, I'm going to look, so basically your connection coefficients are simply, it's the Hessian of U. Okay, the connection coefficient, as I said, is the Hessian of U in direction. So let me use this notation. So E alpha, E beta. So my frame, again, my frame is L, L bar, E1, E2. So I'm taking this notation, E3 is L bar, E4 is L, and then E1, E2 are the other ones. So in other words, all the connection coefficients are of that type. And now I'm going to put another derivative. So now let me take another derivative, so the gamma. And now I'm going to relate the connection coefficient by, for instance, commuting the gamma and the beta or the alpha. Okay, so I'm going to commute two derivatives. And when you commute two derivatives, you're going to relate two connection coefficients. So this, for instance, will be related with, let's say, d beta d2u of E alpha E gamma. Okay, and because you commute, okay, so it's schematic, and there are other terms. I mean, it's a bit more complicated than that, but essentially the idea is there. I'm commuting to, for instance, d gamma and d beta, and because I'm commuting d gamma and d beta, I get a curvature term, which is going to be contracted with all these indices. So you'll have, well, okay, so you have, yeah, I'm going to get the order wrong, so let me not put it, but you'll get a curvature term here, right? Okay, so here I'd like to derive, and I can do this, of course, for all connection coefficients in all directions. So you get tons of relations here, which are referred as null structure equation. So here I'm following I should have said that I'm following the framework introduced by Christodoulou and Klainerman in their celebrated work on the stability of Minkowski spacetime, and they derive all the null structure equation. And here I'm simply going to write down for you the one that I'm going to use because, you know, if not, we're going to spend a whole time just reviewing that. Okay, so let me first start with the easiest one of them, which is the most celebrated, which is the so-called Red-Shadow equation, because that one is of own interest in itself. So Red-Shadow equation is the one where I contract. So I take the trace, so trace chi, which is my mean curvature. So here I contract the Hessian with E1, and then E2, E2, and then I take an L derivative. And when I get this equation, which is L of trace chi is minus 1/2 trace chi square minus chi hat square. So you're going to ask me, why is it that I don't get, so I should in principle get two connection coefficients which are derivative of connection coefficients which are related and a curvature component. So why is it that the second one here is not there and the curvature component is not there? This is simply because when I take an L derivative and I commute the L derivative with the E1 derivative, I get DLL, which is 0. So that explains why this term is 0. It's because you get a DLL here, which is 0. So that takes care of this term. And this one is 0 because you get a contraction of the curvature tensor, which gives you a Ricci term. So you get Ric LL, and the Ricci tensor is 0 by Einstein. Okay, so that's why here there are two cancellations, and you get this magical, very simple equation. Notice in particular that it has a sign. It tells you that if you integrate in the direction of the null geodesic, the mean curvature is decreasing. Okay, that's well, okay. So that's absolutely not important what I'm doing now. It's totally irrelevant, but it's very important in general. In particular, it's important for all these results on formation of trap surfaces. It's important for the so-called singularity theorem of Penrose. So this is a very important equation. But again, I'm not going to use the sign here. I'm just going to use the structure. Okay, and now you see that you have a relation. So the Red-Shadow equation gives you a transport equation for this mean curvature in terms, in particular, of the traceless part of the second frontal form. So I need also to tell you how to control this traceless part. So to control the traceless part, you do another commutation in which you relate the connection coefficient of the traceless part with the mean curvature, and you get well, you get a divergence operator on the two surface. So divergence of your two form chi hat is 1/2 of the gradient of trace chi. Then you get, as usual, you get quadratic terms in the coefficients, Ricci coefficients. So let me not care about this one. But the curvature component you get this time is not 0, and it's the beta term. Okay. So this, I claim, is an elliptic equation on the two surface, because when you take a divergence of a symmetric traceless to tensor on the two surface, it's actually, you can easily check that it's an elliptic operator. In other words, it simply if you look at it carefully, it simplifies in having Laplace equation, Laplace operator of each of the coefficients of this symmetric traceless to matrix. Okay, so it's a straightforward computation. So believe me that this is elliptic, and that you get, in particular, because it's elliptic. Let me just write down the fact that I thought I had to. So it's here. Okay, so let me simply say that because it's an elliptic operator on the two surface, you could just think of it as the following formula, that chi hat is a pseudo-differential operator of order -1. So it's not like, it's a rough operator, so it's not really different. But in essence, it's an operator of order -1. So it gains back a derivative applied to 1/2 of gradient trace chi. And let me forget about the junct term and just put the beta term. There's beta, and then plus blah, blah, blah. Okay, so that's what I want. I want to see how I relate this to another connection coefficient and the curvature. The rest is not so important here. And then I will need another set of equations, the one that relates my mean curvature. I'd like to also estimate the L bar derivative of my mean curvature, and I want to relate it to the torsion. Okay. So here you have another again. So you see, it's always when you decompose it on a frame, you will see always that you get transport equation, which will not surprise in direction L, which will not surprise you because as we have seen, it's a nonlinear transport equation in the direction of L, the econal equation. So these transport equations are natural, and they are always coupled back to elliptic systems on the two surfaces. So that's how you control it. That's the correct way to control it if you don't want to start losing derivative. If you want to work in a rough setting, don't use the method of characteristics. Really go to the Hessian and start decomposing. Okay, and you can. Okay, so for this one, you can also get a system dealing with transport. So you have transport for L bar trace chi coupled with a diff curl system, and therefore it's an elliptic system for the theta term. And here you see that the curvature term that you obtain this time are rho and sigma. So they are further down in the hierarchy because they have more L bar. Okay. Okay. Anyway, so we'll see how you control. Anyway, I want to. I'll start by with this one with the retro equation, how you control the mean curvature. But maybe first, let me give you a last ingredient. So here, I need also something which is going to remind me precisely of the null structure of the Einstein equation. So we have seen that the null structure is very important at the level of controlling the wave equations. When controlling the wave equation, we had to have the null structure on the right-hand side. I claim that the null structure is also very important to control the econal equation. Okay, so that's another place where this structure intervenes a lot, and it intervenes in the form of the so-called Bianchi identities. Okay, so in other words, I will end up having to take derivative of the curvature components, and I'd like to relate derivatives of the curvature component. In particular, remember that there is a hierarchy. Maybe I should talk about it again. You have this frame, and the best direction is always the L direction because that's the direction of the transport. So that should be the best direction. The next good directions are E1, E2 because they are still tangential to the level hypersurfaces of U. And the worst derivative is the L bar. Okay, so this is, let's say this is great, this is good, and this is bad. Okay, just to make things simple. Okay, and this is bad. This we had already a first manifestation of the fact that this is bad is because when you have two contractions of the curvature tensor with L bar, you don't have any control of the curvature flux. I mean, this alpha term, which had 2 L bar and no L, you had no control on it. Okay, so now how do you get? So now I need to see some structure which relates the curvature components together, and these are called the Bianchi identities. So here actually I'm talking about the so-called second Bianchi identity. So remember the curvature tensor has lots of symmetries, and there is something called the second Bianchi identities, which is a differential equation satisfied by the curvature tensor, which means that if I take d tau, so R is a 4 tensor, the Riemann curvature tensor is a 4 tensor, so if you take d tau, R alpha, beta, gamma, delta, and if you write down you sum down over all permutations of the 3 first indices, then you get also d beta r tau alpha gamma delta, d alpha r beta tau gamma delta. If you make this sum over all permutations, you actually get 0. Okay, so that's this by the way has nothing to do with the Einstein equation. This is a general identity satisfied by any curvature tensor on a pseudo-Riemannian manifold, and in particular on Lorentzian manifold hence. Okay, but now the consequence of we want to couple this, and we have already seen this identity. You want to couple this with the Einstein equation, and that's why you get something very interesting. So if you contract this identity, you're going to have some relation. You're going to see if I contract, for instance, the tau with the alpha. Here I'm going to get a divergence term, and then you can see that you get Ricci terms because then you contract within the curvature tensor. So you take a trace of curvature which is Ricci. So here, the Ricci term, they are going to be 0 through Einstein, and you are left with the divergence, which is 0. Okay, so we already used this when we reduced Einstein to a quasi-linear Young-Mills system. So we already used this identity. So again, you get it by contracting and using Einstein equation. Okay, so now I claim this identity somehow encodes, is a good way to encode the null structure at the level of curvature. Okay, so you see what you get when you actually decompose it on the frame. This gives you relation between derivative of some curvature component in some direction and derivative in others. Okay, and in particular, I'm going, so again, you have tons of them. You can write a whole list. But I'm going to simply give you the two ones. These are the two only ones which are going to be relevant to the next slides. So let me just, I mean, we actually, in principle, we use all of them, but in the proof, but let me just specify these two here. So again, you relate derivative of the curvature in some direction with derivative of other curvature component in other direction. So in particular, you see that rho sigma, they always come in pair because they have the same signature. Rho and sigma have signature 0. They have as many L as L bar. So they always come in pair. And then I want to relate them to the beta. So if I take the L, because L is a good direction, I go higher up in the hierarchy. So this is related to beta, which has one more L. And if I take L bar, which is bad, I go down in the hierarchy. So this is related to beta bar, which is one step down in the hierarchy. And what I want to emphasize is that so L of rho sigma is related to the beta here. But in the case of L bar, so and let me not specify the other terms. There are lots of other terms here, but I just want to specify one of them here because it contains the alpha bar. So as soon as you go down from the rho sigma with L bar, you start seeing an alpha bar, which, as we saw, is not in the curvature flux. So that's going to be a problem. Okay. So maybe let me just write down these two relations, and you see that you get for beta and beta bar, you get therefore an elliptic system, because you get a div curl system on the two surfaces. So this is elliptic. So in principle, if things were smooth, you would have somehow a pseudo differential operator of order -1 if you want. So let me write it in that way. So I have L of rho. Okay, so no, sorry, let me write it in that way. So I have beta. So this allows me to write beta as d -1 of L of rho, and minus L of sigma. Oh, right, let me actually write it like this, L of rho minus sigma. Okay, plus other term, let me not specify. And I'd like to write down also the beta bar term, which is a d -1, but this time you have, what is that? You have L, sorry, so you have L bar of rho minus sigma. And then you also have this junct term, which is d -1 of chi hat alpha bar. Yeah. Chi hat alpha bar. Well, let me not specify the alpha bar star. Well, actually, I could specify. It doesn't matter. Okay, but anyway, the important thing is that you have an alpha bar here. Okay, so in terms of structure, this is roughly what you see. There are other terms, but let me just not specify them. Okay, so now you are all set to actually start analyzing the system. And again, everything reduces to coupling between transport equation and elliptic systems on the two surfaces. Transport along L and elliptic system along the two surfaces. So I'd like to start with estimating trace chi in L infinity. So in other words, I'd like to show that the mean curvature is in L infinity. We'll see later that this is the, in some sense, this is this is the crucial estimate in some sense. I mean, the other ones are also important, but in some sense, if you don't have this estimate, everything collapses. Okay, so and we'll see. Well, we'll see later. I'll explain. I give a very specific later on why this collapses. Okay, so I want to control the mean curvature. Remember, the mean curvature is the symbol of my error term in my parametrics. And I'd like to control it in L infinity. You can actually also, from that point of view, you can see that this is absolutely needed. You need much more, but this is absolutely needed. And remember, this satisfies the so-called Red-Chadori equation, which is a transport equation in the direction of L. So the good thing with transport is that you cannot really gain something, so either it's there or it's not. And therefore, I just have to integrate stupidly. I get trace chi is controlled by the initial data of trace chi, and I talk about what I mean by I talk about the initial data later on. I didn't talk about this issue yet, but that's for later. But anyway, the important thing is that here on the right-hand side you have two terms. So here again, remember you're integrating, this is L, so you're integrating along the null geodesics. And remember, I have parameterized my null geodesics by this affine parameter S. So this means simply, this has nothing to do with coordinates. It's an invariant. This means integrating along null geodesics. Okay, that's it. Okay, so I want to integrate along null geodesics, and then I want to claim that once I have integrated along null geodesics, I see something in L infinity. Okay. And of course, I have this term here, and now we have. Remember that this term is given by the Kodazzi equation. So if I take Kodazzi, I can relate this term back to trace chi, and now also to the beta term. So chi hat, if this is an elliptic system on the two surface, so I can invert this elliptic system. Here I have a gradient, so I have a d-1 of gradient, which is a d0. So essentially, it's a pseudo-differential operator for the 0, if you forget about the problem of smoothness here. And then this would be a d-1. So this gives back one derivative from the beta. Okay, and then you have the junk. So now if I come back to my relation, if I integrate this chi hat along the square along the null geodesic, I get this term involving the mean curvature with the pseudo-differential operator for the 0. And then I have an operator for the -1 applied to beta square along the null geodesic. So if I plug this back in the formula for the mean curvature, I see that the integral of the I see that trace chi is controlled. So let me forget about the initial data. I'll talk about it later. So let me simply put these two terms here, the d0 of trace chi square and the d-1 of beta square. Okay, so I have d0 of the mean curvature and d-1 of a certain curvature component, which is beta. And of course, here it's important that it's beta and not anything else, and we'll see why. Okay, so here at this point, I'd like to point out that if you didn't have the null structure, this estimate would be, you would not conclude from this estimate. So let me just convince you first that this estimate as it is not, it's not correct. You need structure to get trace chi in L infinity. Okay, so I'd like to talk about this term here. So how do you control this term? How do you get L infinity? So what, so this I don't need. Okay, so let me simplify to the flat case so that we understand what's going on. So in the flat case, I would call, so for instance, let me think of the flat case where HU is a hyperplane. Let me call this direction. So this variable will be the S variable. And now let me call the tangential variables of PSU. So this is PSU. Let me call these variables X prime. Okay, so X prime are the tangential. X prime is X1, X2 are tangential variables. So let me I'm not supposed to use coordinates at this stage. We're doing everything invariantly, but just for the sake of understanding what's going on, in the flat case, let me take X prime, X1, X2 to be the variable which parameterize my two-surface PSU, and let me S parameterizes the null geodesic. Okay, let me do just work in this coordinate so that you can understand what's going on. Okay, so here, here I'm integrating along S. So I'm integrating this along S. I'm integrating d-1 beta square along S. So let me write this like this. I'm doing, this is S X prime. I'm doing ds here, let's say from, well, to fix ideas from 0 to 1 for simplicity. And then I'm taking the soup in X prime. So now I'm going to say that X prime is in R2. Okay? So essentially, in this coordinate system, I'm having a function of R3, which I integrate along one variable. I square it, sorry. I integrate along one variable, and I take the soup with respect to two other variables. So that's a very well-known estimate. That's just a trace estimate. So I'm asking you whether if I take a function, I square it, and I take the soup, I'm asking you whether you get the following estimate. So what is the estimate that I know? I know that if I take one derivative of this guy, I'm back to the beta, which is L2 along HU. So I'm asking you whether this is controlled by this, well, a derivative, in other words, a derivative of d minus 1 beta of fx prime L2. Right? Because if I had this, this would be simply, because I have dd minus 1, this would be essentially the beta. So this would be exactly what I called beta, the L2 norm of beta along HU. And we have seen that this guy is in the curvature flux, so this one is under control. Okay? So if this estimate was correct, I would be done. The only problem is that this estimate is obviously wrong even in the flat case. This trace estimate, you're simply doing, this estimate exactly means that you're requiring H1 of R3 to embed in L infinity of R2 with values in H1 of R. Right? So this, sorry, yeah, you don't, I'm not sure if you see, let me write it. Let me write it here. So you're having H1 of R, no, sorry, you're having H1 of R2, no, it was wrong. Yeah? It's H1 of R3, and you're trying to embed it in, sorry, it's L infinity of R2 with values in L2 of R. That's what you're doing, yeah. Okay, so this estimate is borderline, right? This estimate is wrong, simply because the trace estimate loses one half derivative per dimension, right? The trace estimate, when you do the trace estimate, so here I'm doing the trace estimate with respect to two variables, to two dimensions. Okay, when you do the trace estimate, you lose one half derivative per dimension. So this dimensionally is correct because I go from H1, I lose half a derivative, I go to H1 half. I do again the trace estimate for the other variable, x1 and x2, let's say, and I go to L2. So dimensionally it's correct. I go from H1 to L2, I lose half a derivative per dimension, so that's correct. But of course, you know the trace estimate, that's the borderline case, right? It's like H1 half does not embed in L2 of the boundary. So this estimate is wrong, right? So let me write down what is the correct estimate. So what is the correct estimate? The correct estimate is the following. The correct estimate is H2. I just have to take more to go to higher derivatives. So I'm asking whether H2 of R3 embeds in L infinity of R2 with values in H1 of R. But this one now, this is the correct one. So this is the one that I want to use. In other words, I want to argue that, so what is it that you want to achieve here? You want to say that this guy, so in other words, I want to, I'm wondering whether this guy, d minus 1 of beta, whether I can write it as a derivative, so a tangential derivative. So now along my null geodesic, the tangential derivative is L, as an L of a function which itself is in H2. Okay, so in other words, it's just a matter, this is a matter of structure. If instead of having a d minus 1 beta, I had an L of d minus 2 beta, I would be fine, right? I'm asking, so in other words, I'm asking the following thing. If I want to use the correct trace estimate, so I want to ask whether in terms of structure, I have d minus 1 beta is L of d minus 2 beta. Okay, so in other words, I want, if it was L of d minus 2 beta, then this would be essentially in H2, and I would take a tangential derivative of something in H2, so it would be exactly corresponding to L infinity H1 of R. Okay, so it's just a matter of structure. It would be the correct trace estimate if instead of having d minus 1 beta, I had L d minus 2 beta. Okay, that's fine? Okay, so it's a matter, so in other words here, it's not the regularity that's under concern, it's the structure of the equations. So you're hoping that there is something magical with the structure, and I claim that this is just Bianchi. This is Bianchi that tells you that. Okay, so here, this is where you see the structure of the Einstein equation. You use the Bianchi, so you remember this. In other words, I want to use this. I want to use that B is d minus 1 L of rho minus sigma, and therefore, I have d minus 1 beta is d minus 2 L rho minus sigma, and if I commute them, assume that commutation is fine, I get dl of d minus 2 rho minus sigma. Okay, so that's my that's my function in H2 because I get back two derivatives, and but here I have a dl derivative. So in other words, I'm using the correct trace estimate. Now, if I ask you if this is in L infinity, well, this is controlled by a 1 L derivative of f. So in other words, I'm trying to control the H1 norm on the boundary by the H2 norm on the whole space, and that's the correct trace estimate. Okay? Okay. Okay. So let me finish by making two remarks. So first of all, again, let me emphasize that you see at this stage, it's crucial that you have the null structure. Here you see them in the form of the Bianchi identities coupled to the Einstein equation. If I didn't have that structure, I would have a borderline trace. I would have a problem with my trace equation. So here it's not a matter of regularity, it's a matter of structure, which saved us in the end. Okay, so I wanted to emphasize again that the null structure is not only used for the wave equation, it's also used for the econal equation. Okay, now I'd like to talk about two caveats here in this proof. I'd like to come back to the fact that you have this D0 trace chi term here. This obviously, from the start, my estimate is wrong because pseudo-differential operator for the 0 do not map an infinity in self. So this forces you to go for more. Okay, it's always the same business. Because it doesn't work, I have to go for slightly more. So actually, what you have to prove is a Buzz-off improvement of that estimate. Okay? And okay, so you go for a Buzz-off improvement, which this time you go to a Buzz-off space, which is at the same level as L infinity, but this time this Buzz-off space has correct mapping by pseudo-differential operator of theta 0. Let me not go further on that. And I'd like also to say that the other thing which is important here is that you have lots of, so I talked about the commutation between these two guys as being a lower order. It's actually not true. It's not really what happened. The commutator between this guy and this guy gives you a term which is as bad as this one. The only thing you gain is the size. So this is quite typical of critical problems. So that means that you need to do an infinite normalization. In other words, I need to do the next trick for the next term and write it also as DL of something. And I do it infinitely many times in the sequence until the size becomes smaller and smaller and vanishes. Okay, so you do, if you want to, you write it is in the same form as this, but as an infinite converging sequence of terms of that type. Yeah, I guess it's good to stop here. Maybe continue after. So, I mean, now that we have this estimate for the mean curvature in L infinity, I'm going to go a bit further in the analysis, but I'd like maybe to quickly review the equation to refresh your memory. So just remember that we have started with the solution of the econal equation. We have decomposed it. I mean, we have decomposed the Hessian. We have introduced this connection coefficient, which is nothing but looking at the Hessian of u in several evaluated in several directions. In particular, I have isolated two important connection coefficients, which is the second fundamental form and the torsion. And we have decomposed the curvature on the frame adapted to this econal equation, which is this null frame L bar E1 E2. And in particular, we have used, and we're going to continue to use this null structure equation, where you see that you get each time systems which are coupling transport equation along the null geodesics, so it's transport along L, with elliptic system on two surfaces. And the important thing is that the way you use the Einstein equation in this system, the way you see the Einstein equation is because this system, they have on the right-hand side the curvature. So the curvature is feeding this transport elliptic system. Okay, so you feed the transport elliptic system by curvature, and curvature satisfies the. I mean, it's the curvature coming from your solution of the Einstein equation. So that's the relation between your econal equation and the Einstein equation, and in particular the fact that you have this Bianchi identities, which gives you a certain relation between the curvature components. This is how you exploit. This is how you see the null structure of the Einstein equation, and this is how we were in particular able to exploit here this Bianchi identity to obtain that trace case in L infinity by removing a log loss in the trace estimate. Okay, so now we have this mean curvature in L infinity, and I'd like to continue with further studying other components and other components of the other derivatives or other components, other connection coefficients. Sorry. Okay, so let me briefly discuss other estimates still in space-time. So here, so far, I'm only considering omega as a parameter. You can even forget that there's an omega for all these estimates. Omega is totally irrelevant. It's going to be relevant in the next slide. But for now, let me conclude the estimates which have to do only with derivative respect to direction of space-time, so not with the omega parameter. So here omega, you can still forget about it, and I'd like to conclude quickly on this, on how you proceed for the other derivatives. So first of all, no, actually, I have still something else to say. Anyway, okay. So first, you have another. So here, so far, I have used the coupling, the coupling between the transport equation for trace chi, which is called Ricciardo. So this is blah blah blah, and I have a coupling with the Codazzi equation for the traceless part. So I use this transport elliptic system, but we have seen that there is another coupling between the transport and elliptic system, which relates L bar, another derivative of the Ricci coefficient, which is L bar trace chi. It relates L bar of trace chi with, there's a diff curl system for the torsion for theta. Okay, so it turns out that you can analyze this this other elliptic coupling between transport and elliptic system in the same way that you analyze in similar way that you analyze the coupling between trace chi and chi hat. And therefore, by similar argument, you're also able to get a corresponding control for L bar trace chi and the torsion theta. Then, if I want to get angular derivative of the mean curvature, I just have, this is very easy. I just have to differentiate the Ricciardo equation by an angular derivative and commute, and I will be able to control this. And then again, all the others. So there are still other connection coefficients which I did not specify, but all of them you can again get them by transport and elliptic equations. Okay, there is another thing that I'm not going to mention at all, but you also have to control the time foliation. So this only takes care, all these arguments take care of the U foliation, so the foliation of the spacetime by null hypersurfaces, which are level sets of U. But I have another scalar function, which is the time function. So let me not talk too much about it. Let me actually not talk at all about it. But you have this level, you have the foliation by time, by the time functions. And since I also use this foliation for energy estimate, I do need to control it. And so, in particular, I do need to control the second frontal form K of the embedding of this level set. Okay, so this is nothing. So you also have to. Well, let me not say what is the. So the time lapse here is just the infinitesimal. It's the foliation density. So it's the infinitesimal distance between two leaves of the foliation, but you also need to control second frontal form. Okay, so this is something extra you have to do. And now I'd like to come. I'd like to make a connection with something I said yesterday, which is the criticality which is in this result, which is the fact that you cannot expect to control the econal equation without curvature in L2. Okay, so I think we saw already so far. So in connection with this criticality of the control of the econal equation, let me remind you that so far we have seen that curvature in L2 is needed to control, to have trace chi in L infinity. And not only that, but we've seen in the previous slide, we've seen that you have to use the trace estimate. It's sharp, but not only it's sharp, it's borderline. So it was even not. It's needed, but it's not even enough. To get this estimate, we also had to use the null structure of the Einstein equation. Okay, but certainly we saw that we used the sharp trace estimate. We lost exactly 1/2 derivative per dimension. So there is absolutely no room in that estimate. Okay, so I hope I convince you that curvature in L2 is absolutely needed to have the mean curvature in L infinity. And again, I also convince you that it only works because you have the nice structure of the Einstein equation. So now I'd like to come back to the issue of what is the minimal regularity to control the econal equation. So far I convinced you of this, but maybe you could tell me that after all, the mean curvature in L infinity is maybe not needed, and you could do something with weaker quantities. Okay? So here I'd like to argue that actually it's not the case. That if you want to control the econal equation, this estimate is actually absolutely fundamental. Okay, so let me tell you why. So you have now, let me remind you also that this is a nonlinear transport equation, and we have seen that you could, in principle, construct it from the classical method, which is the method of characteristics. So here, the method of characteristics, of course, as you know, it can break down when the characteristics meet. Okay, so that's why, you know, when you classically do the study, the method of characteristics, you know that if I start with a characteristic, so U is constant along characteristic, and I have an issue, of course, if at some later time the characteristic meet. Okay, so here I'm looking at the level hypersurfaces of U, and in particular they are spanned by these characteristics which we have seen are the null geodesics. And here I'm trying to control it between sigma 0 and sigma 1. I remind you that we rescale things to go from, we rescale our time to go from 0 to 1. So I'd like to control, I have to control my foliation at least until time 1, and I would be in big trouble if I had two characteristics, or in other words, two null geodesics meeting before that, okay? And in particular, I also like to mention that this, in principle, has nothing to do with regularity. The method of characteristics could break in a smooth background. It's not, the fact that two null geodesics meet is a feature of the global geometry, not really of the local regularity. Regularity is local, but here it's more a global thing. I could have two geometrics that are far away and they still meet. Okay, so this is about not regularity but global geometry of your space-time. Okay, and yeah, what do I want to say? Sorry. Yeah. Okay, so so when these characteristics meet, actually it's classically known as what is called a caustic. Okay, so you have to prevent caustics from forming before time 1. Okay, so how you do this? So first, let me tell you that there are two things going on here. So I said this is a global thing. It's not quite true. There is also a local statement about characteristics non-crossing. In that case, it's null geodesics. So two null geodesics far away, of course, this is a global statement, but very close away, if I take infinitely close geodesics and I require them not to cross at later time, that's what is called the radius of conjugacy. Okay, so you are two things with geodesics. Geodesics not crossing is called the radius of injectivity, but if you take infinitely close geodesics, for instance, if I take two geodesics like this, they are almost the same, and I ask them not to refocus later on, at least until time 1. That's what is called the radius of conjugacy. So I need to control first the basic thing, which is radius of conjugacy, and then I need to control also the radius of injectivity, because I cannot allow them to cross even if they are far away. That would still lead to a caustic. That would be a problem. Okay? So I claim that the radius of conjugacy is actually, so this obviously is something local, so that should be controlled by regularity. And indeed, you can actually check that it's precisely mean curvature in L infinity that controls the radius of conjugacy. Okay, so it's actually essentially equal. If you try to control, you can actually derive an ODE. It's known that you can derive an ODE for the distance between two infinitely close geodesics, and that ODE is actually controlled by trace chi in L infinity. Okay, so far we did half of the job, if you want, by getting this estimate. We are controlling the radius of injectivity, of conjugacy, and this I claim, of course, controlling the radius of conjugacy is crucial to control the econal equation and to prevent caustics from forming. Okay, so for that reason, because we have seen that curvature in L2 is absolutely needed to get mean curvature in L infinity, and because mean curvature in L infinity is needed to get radius of conjugacy, therefore, if you are to get to construct a solution of the econal equation, you certainly need crucially that bound. Okay, so for that reason, this regularity is minimal to control the econal equation. And if you are to go below the result I'm presenting in these lectures, then you would have to find a way to somehow bypass the econal equation. Which, I mean, it's hard to think, but who knows? I mean, I just. Anyway, and then I'd like to also talk about how you actually control the radius of injectivity, because so far we only have the radius of conjugacy, and as I told you, the radius of injectivity is more of a global statement. So the question is, how are you preventing faraway characteristics from forming? And here, actually, I'd like to argue that again you can relate it to a local estimate. And so let me just draw a picture of what would happen if you had two null geodesics crossing at a later time. Okay, yeah, I guess I can erase. Okay, so what is the obstruction? What is the global obstruction of your foliation? So in other words, I need to hope that my foliation has a good behavior such that it has a good global behavior which prevents this crossing of null geodesics. Okay, and again, this part is a very classical thing. I mean, this is something you have to do even in a smooth case, right? You always have to prevent that from happening. Okay, so let me assume that two geodesics cross. Okay, so I have this. So at a later time, let me assume it's before time 1. Okay, so then, okay, so how am I drawing this? Yeah, actually, yeah, okay, no, it's not going to be easy to draw it like this. So let me draw it differently, sorry. So if you had a geodesic which crosses, so let me take the first time where a geodesic crosses. So then that's, okay, let me fold, I mean, my HU would fold like this, right? Because you would have, okay. So let me finish the drawing, it's going to become clearer. So so that's my HU. And my HU now, because, right? Because I have two null geodesics that meet, it has to fold that way, right? And where the null geodesics are these ones, right? Let me just draw them. Okay, so two null geodesics, they are different, but they meet at that point. So they are on each side of this folding, right? So this is one null geodesic, this is the other one. Okay, so here, of course, so by itself, if I didn't have a foliation, I wouldn't get a contradiction. It's very important to have a whole foliation of spacetime. Actually, one of the things you have to prove is that for each sigma t, you can foliate the whole. So that's a sigma. I'm taking a fixed time, right? I'm taking the first time. This is the first time where I have geodesic crossing. So let's call it sigma t 0. So I need to make sure at each time that I can foliate the whole slice sigma t by this HU. So that's very important. And I claim that the only contradiction comes from having a whole foliation. If not, you wouldn't get any contradiction. So let me draw other slices. So the point is that my other slices of the foliation, they also have, because I'm foliating the whole space-time, in particular, I'm foliating the interior region here. And because my slices at infinity, they go to infinity, this is something I have to control. Somehow, I don't have really much of a choice. My slice also has to go through this snake and to exit. So in other words, it also goes through that neck. Okay, so it has to come from infinity and go through that neck. So there's not much choice. It has to go like that. I mean, it's a 3D situation. I mean, it's not. Well, okay, I'm cheating a little bit because it's 3D situation. So it's in effect, it's actually more complicated than that. But let me just give you a simple argument, which I think it's convincing. So it's not quite what I'm doing here is not quite what you prove, but because it would be actually difficult to prove that this is what happens. But at least I think from a visual point of view, it's easy to understand that something like this, in principle, should be there. Okay, now you see where the problem is the fact that there is a local quantity here which breaks down. I mean, of course, this is global, but because I have full foliation, there is also something local which breaks down, which is the fact that if I look at this infinitesimal distance between these guys, which I'm going to call B, which is the inverse foliation density. So I have this quantity which is also related actually you can relate this quantity to 1 over the gradient of U, where this is the gradient on sigma t, right? Sorry, I should write it larger. So B is 1 over the gradient of U. That's the lapse. That's the lapse of the U foliation. And that guy measures, so this is the covariant gradient on sigma t. This guy measures the distance on sigma t between two, infinitesimal distance between two members of the foliation, okay? And this guy now is a local quantity because it's an infinite distance. And I do have a transport equation for this guy, which allows me to say that this guy is close to 1. I'm starting with a nice foliation. So a nice foliation is a foliation where B is equal to 1. If you think in terms of the hyperplane, you compute this B, and I think we've seen in the Strickland's estimate that this guy is exactly 1. So a nice foliation is B is equal to 1. These are slices of the foliation which are nicely separated, okay? And I'm starting with B is equal to 1, and because of the control that I have on B, I am able to show that this is transported, that B stays close to 1. And therefore, you see a problem. Of course, at the neck, there's a problem. At the neck, you have to have B is equal to 0 because your foliation is infinitely dense, okay? So there is obviously a contradiction between the estimate you are able. So in other words, before the first collapse, all my estimates are correct, and I am able to control B is close to 1. So it's not possible that at the time of the collapse, suddenly I get B is equal to 0. Okay, well, it's not. It's an argument with the hands. I'm waving hands. It's not exactly the way we prove things, but it's just to have an idea of why, when you have a whole foliation, which starts regular, you get some global information out of it. So again, I'd like to point out that I cannot make this argument with only one leaf of the foliation. I need the whole foliation. Okay. Okay, so that's it. That's what I wanted to say. I still need one additional estimate about a very bad quantity. So again, I said that the L bar derivative is the bad derivative. We have seen that we have an estimate for L bar trace chi. I'd like to derive an estimate for that quantity because unfortunately, this quantity comes up when you try to control the parametrics, which we'll do this afternoon. And it turns, so this, of course, is a very bad quantity because it has 2 L bar. And the only thing I want here is any estimate. Anything, if I can say anything, I'll be fine. But even saying anything is already problematic at this stage. Okay, so let me recall the system that you have. So now I'm analyzing the system that gives me the L bar trace chi. So let me recall you that at first you have the following thing. Okay, so at first you have the following system. You have L of L bar trace chi is equal to, and then you have this term which is, before I differentiate, I had this term which is minus 2 chi hat times the derivative of the torsion, times the tangential derivative of the torsion. So that's the system you have. We have derived this system, and we have also derived seen that you have the following elliptic system, which is a div-curl system for the torsion. So we have div theta, I think it's 1/2 L bar trace chi. And then you have blah, blah, and then you have a minus rho. And then you have curled theta. Okay, so I'm simply rewriting the system I told you some slides ago. Okay, so this is one of the null structure. You have a coupled system. So again, it's a coupled system with transport along L and an elliptic system on the two surface, which couples L bar trace chi in the torsion. Okay, so now I want to differentiate one more time against L bar, and you can immediately see what is the problem. So first of all, if I differentiate one more time, therefore up to commutation, I get L of L bar trace chi. Let me forget about the commutator. And then if I differentiate this term here, I get two types of terms. One when the L bar falls on the torsion. Again, let me forget about the commutation. And one when the L bar falls on the chi hat. Okay, and then you have other terms. And here, if you differentiate, you get L bar trace chi, but you also get L bar rho and L bar sigma, and that's where you start, you start seeing the bad term alpha bar. Okay, that alpha bar is always the one you don't want to see, but unfortunately, at this stage, there is no way to avoid it. Okay, so you have this alpha bar, which is not controlled by curvature flux. What saves you, of course, is that it doesn't have a derivative, so there is still something to gain here, but it's not going to be great. Okay. Okay, so here you have. Okay, so yeah, I should So if you plug this back in, you see the following thing. Maybe I should write this. So if you plug this back in the theta term, you see you have a derivative of theta which appear here. So derivative of L bar theta. So in other words, from the equation and the Bianchi, from the equation for L bar theta and the Bianchi identities, I get that a derivative of one derivative of theta essentially is like a tangential derivative of a beta bar plus a chi hat alpha bar. So this is schematic, of course. Actually, there's a d0. Well, okay, there's a zero order term here, and then blah blah blah. Okay, so you have you solve your elliptic system. You solve this elliptic system. You use the Bianchi, and you get this. Okay, and then if I go back to this equation here and I plug this back in, I see in particular a term. So I see the following. I see L of L bar trace chi, and here I see the following term. So you have a chi hat. So you have chi hat times d0. So d0 one gradient. It's a d1 beta. You have chi hat, chi hat, let's say chi hat square alpha bar to simplify. And then you have the other term, which is a derivative. You have a derivative of chi hat times a tangential derivative of theta. Okay, so let me roughly tell you why you should expect this estimate. So here you should expect the following estimate. First of all, because you have the transport, you integrate donc your null geodesic. So what if you're able to get an estimate, you should just integrate back something which is L infinity with respect to S variable, which is my parameter, my affine parameter for the geodesic. I integrate in S, so I should expect something L infinity in S. And then the other thing, you see that you have here that you have one derivative of beta. Beta is in L2 from the curvature flux. So this you should expect to be H minus 1. This is bad. It's not in the curvature flux, so the best you can do is just L2 in M. So it's L2 with respect to all variables and not L infinity in U. So it's L2U, L2x prime. And this is L2 times L2 because the connection coefficients, one derivative of the connection coefficient is in L2. So L2 times L2 is in L1. Okay, so this explains the following estimate. The H minus 1 comes from the beta, the derivative of beta. This estimate, the L1, comes from the product here, which is L2 times L2, so that gives you L1. And finally, the alpha term, so the alpha term here gives you the fact that you're not L infinity in U, but only L2 because you're not in the curvature flux. But because it doesn't have a derivative, you lose a little bit less. You cannot quite get L2, but you get H minus 1 half. Okay, so of course, in some sense, it's a very bad estimate. It's an estimate that basically tells you, I mean, at least this term, philosophically, you should understand this estimate. This term is like if you would replace L bar by an angular derivative. Okay, essentially, you're losing the structure. So you're paying the price of having two additional terms here. But basically, this is the same regularity, right? If I give you this term here, one angular derivative of L bar trace chi, because L bar trace chi is in L2, you get this guy in H minus 1. So you should understand this estimate as I'm almost able to replace one L bar with one angular derivative. And in this business, when you replace a bad derivative by a good derivative, it's always because you use Bianchi somewhere. So here, we had to use Bianchi here. That's the null structure that you're using to get this estimate, and you're paying the price of having two additional terms. So at least you're getting an estimate. So here, let me, I'm writing down this estimate because we'll use it this afternoon, but let me just say that, okay, so of course I'm cheating, so in particular I cannot quite get L infinity in S because of integration by parts that needs to be done. And it's also, I'd like to say also this estimate is it's a borderline estimate. So all these products, these things that I'm claiming, I still need to take products there, and they are borderline, so you cannot quite close it at the level of usual spaces. You have to replace little L2 based spaces by little L infinity. So you have to go to weaker Bezoff spaces. So for trace chi, we had to go to stronger Bezoff spaces. Here it's the contrary. You have to go to weaker Bezoff analogs of L2 based spaces. Anyway, okay. So this is what it is. And now I'd like to mention what's happened with respect to omega, because I think that's actually quite an interesting story. So you have your econal equation. So far, I've only mentioned regularity with respect to derivative in space-time. Now I want to remember that I have this parameter omega, because dependence in omega is going to be important. It's actually quite interesting to see that this dependence is much more complicated than what you would expect at first. Okay, so let me first explain you why you could think in first approximation that the omega dependence is essentially trivial. I mean, in terms of regularity. So if I look at my econal equation, remember I have G alpha beta, D alpha U, D beta U is equal to 0. So in particular, omega is only a parameter which describes the asymptotic behavior of the econal equation at infinity. So it has nothing to do with the metric. The spacetime is fixed. I mean, the spacetime is independent of omega. Omega is only for the asymptotic behavior of U. So in particular, this guy is independent of omega. I mean, this guy has nothing to do with omega, because this guy is the metric of the spacetime. Okay? So the interesting thing is that at this stage, of course, nothing prevents you from differentiating this equation as much as you want with respect to omega, because this guy is independent of omega, so it's infinity in the omega if you want. And this guy is the guy limiting the regularity because the curvature is in L2. So here, question, why is it that you can't differentiate as much as you want in omega. What could be the problem? There is no problem with the regularity of the spacetime. Spacetime does not see omega, so in principle, it seems I can differentiate as much as I want. But of course, there is a caveat here, which is the fact that this is a transport equation. And not only it's a transport equation, it's a nonlinear transport equation. It's a nonlinear transport equation in the direction of the gradient of u. Okay, the transport equation has the following feature that it always gives you more in the direction of the transport. You always have more regularity. You always have one more derivative in the direction of the transport. Okay? So the problem is once I start differentiating, because the transport is nonlinear in the direction of u, so the direction of the transport depends on omega, the derivative is going to fall on the direction of the transport. That's going to rotate it because it depends on omega, and you're going to transfer a good derivative in a bad derivative. Okay? And that's why you start losing derivative. And because you lose derivative, that's what prevents you from differentiating with respect to omega as much as you want. And we'll see that actually differentiating to omega costs you quite a lot. Okay, so let me be more down to earth, and let me show you why you have a problem. Okay, so let me remind you. So let me show why differentiating in omega is costing you much more than what you would think at first. Okay, so remember you have the Ricciardo equation. So let me explain this at the level of the mean curvature. So you have the Ricciardo equation, which is minus 1/2 trace chi square minus chi hat square. And let me just focus on this part of the equation. Let me not even care about the right-hand side. I claim that the problem is with the direction of the transport, so it's the left-hand side. So this equation now I want to differentiate with respect to omega. And therefore, I'm going to pick up the commutator between L and omega. So it's written here. I get L of d omega trace chi, and then I pick up the commutator between L and d omega trace chi. And again, as I said, this is where you have the problem. You have the problem because, indeed, L depends on omega. So when you do this, you pick a derivative of L with respect to omega. So that's not the issue. But the issue is that the derivative d omega L, because GLL, right? Because GLL is 0, you have GLL is equal to 0. So automatically, if I differentiate it, I get GL d omega L is equal to 0. Well, actually, it's not. Yeah, okay. Let me do the proof differently because in that here it's a bit. Okay, so let me write again. Let me normalize L again as t plus n. Okay, so I have my time foliation, which has nothing to do with omega. So I have sigma t. I have my time foliation. I have the unit normal, and I write L as t plus n. Okay, then t is related to the time foliation. It has nothing to do with omega, so that guy does not depend on omega. So if I look at d omega L, it's equal to d omega n. Now d omega n, because n is a normal vector, you have g and n is equal to 1. That implies that g of n d omega n is equal to 0. And this actually encodes the fact that d omega n, or if you want d omega L, this encodes the fact that d omega L is a tangent vector, so it's tangent to the two surfaces. Okay, so you get this term here, which is an angular derivative of trace chi. Okay, so it means that d omega trace chi by transport is related to angular derivative, so you will never, because it's transport does not gain any regularity, so you are doomed with having to say that d omega trace chi essentially is at the same level of regularity as one angular derivative of trace chi. Okay, so you see that differentiating with respect to omega does lose one derivative as a space-time. I mean, it costs you as much as a space-time relativity. Okay. So this is the remark I wanted to say, and then I want to mention that yet again, using the structure of the equation, there is something interesting going on. Is that it's the only way to lose derivative. The only way to lose derivative is by commutation between L and d omega. Okay. In particular, so there are two things going on. Sorry, I should mention. So in this equation, there are two things going on. You lose on one hand derivative because of the curvature tensor, which is in L2. On the other hand, you lose derivative because of this nonlinear transport, so that the commutator between d omega and the direction of the transport is bad. So these are the two only ways to lose derivative, and they are in a sense complementary. I want to convince you that you can do decompositions where on one part only uses for one reason, and the other part only uses for the other reason. You are not, if you want, you are not penalized twice by each of them. They penalize you, but on different parts of the equation, and that's what saves the day in the end. So let me show you this on one component of the equation, which is the traceless part. I want to convince you that the traceless part, you can decompose it in two pieces where each one loses for a different reason, but there is no piece that loses twice, if you want. Okay? So let me remind you that this traceless part satisfies the Kodazzi equation of the following type. Yes, no, this I don't need. So we have related, the Kodazzi equation relates you chi hat. So you have, what is it? You have divergence of chi hat is equal to gradient 1/2 gradient trace chi minus beta, and then let's forget about the rest. So you have the curvature term. So these are the two terms. I'm claiming that these are the two terms that are going to penalize you, but for different reasons. Okay. So let me write. So this is because it's an elliptic operator. I can invert it, so you get d minus 1 of this gradient trace chi. So d minus 1 of gradient trace chi is going to give you d0 trace chi. So that's a d0 trace chi. And this one is a d minus 1 beta. And that I'm going to call chi1, and that I'm going to call chi2. Okay, so the good thing is that one of them is penalized for one reason, the other one for another reason. Okay, so I'm claiming that each of them is actually better than chi hat for a different reason. This one is better than chi hat because the mean curvature, it's related directly to the mean curvature, but the mean curvature, you see in chi hat, if I look in space regularity, so let me first talk about space-time regularity. For space-time regularity, the guy which kills you for the traceless part is the beta term, because it's less good than, because you have transport, you always have more regularity for this guy than for this guy. So in terms of space-time, this guy is the one that kills you, and therefore that means that chi1 is better. So chi1 is more regular than chi hat because it only involves trace chi and not the beta term. So this one is more regular with respect to space-time derivatives. So now I'd like to argue that this one is better with respect to the d omega derivative, so that you see the splitting where you only pay the price once. Okay? So this guy is better simply because the curvature tensor, again, is independent of omega. So the curvature tensor is bad with respect to Tx regularity, but with respect to omega, it's actually independent. It's smooth with respect to omega. So here, you're going to pay. You're not going to pay the price when you start differentiating in omega, simply because if you differentiate, what happens if you differentiate beta? Well, it's very easy. If you differentiate beta, remember that beta is 1/2 of r L bar. Sorry, okay, I'm going to get it wrong. It's A L bar L. So when I differentiate d omega beta, r is independent of omega. You only differentiate the frame. So you only, if you want, the only problem you could face is that when you start differentiating the frame, because you pick different component of the curvature, you pick the alpha bar. If you don't pick the alpha bar, actually differentiating in omega doesn't cost you even one thing. It doesn't cost you anything. Actually, it does cost you because you commutator with this guy, but at least this guy, you don't pay a price, okay? And this is actually what happens if you do d omega beta, you look at the derivative of the frame. So you see if I do d omega beta, r is independent, I just get derivative of L bar, and L. And if you compute what you get, you actually obtain you obtain other curvature components, but you don't get the alpha bar. Actually, you can check that you go in the hierarchy I explained. You go one step down in the hierarchy. So from the beta, the worst that you can get is beta and sigma. Okay, so you don't get the alpha bar, and for that reason, you are better behaved with respect to omega. Okay, so you get a decomposition where this guy is better in regularity in Tx. But as bad as chi hat in d omega, and this guy is better with respect to omega, but as bad with respect to Tx. Okay, so again, you have this splitting where each guy pays the price once, but not twice. Okay, so I'd like to come to, right. No, I still have 20 minutes, right? Okay, good. Okay, so that's good. So then I can come to this last part. So so far, I explained you how to get the estimates for the diagonal equation in space-time, but I still need to tell you something. It's a transport equation, so of course I need to tell you what I'm picking at initial time. There is still one choice that I did not discuss, is how I am allowed to make a choice for the solution of the equational equation at initial time, that is on sigma naught. And this is also, I think, a very interesting issue because it's actually, because you're very restricted in regularity, you will have to make a choice which is actually quite surprising. I mean, if you're used to the lax parametrics of geometric optics, you know that the correct choice. So again, you have an equal equation that's a transport equation. So I'm transporting along null geodesics. So let's say that if I start with sigma 0, so let me go sigma 0 I base. So you have sigma 0, and from sigma 0, you transport along null geodesics. You transport u along null geodesics. So I need to tell you what is u on sigma 0. Okay? Once I tell you this, because it's a transport equation, u will be defined space-time, I still need to tell you this. Okay? So how do you make this choice? Well, let me first tell you what is the usual choice. I mean, to choose u0, so first of all, the only thing I told you is that u has to be asymptotic to x dot omega, and of course, the usual choice. The usual choice assumes that you have a given coordinate system and that you choose u of t, u of 0 x omega, which is u restricted to sigma naught, is equal to x dot omega, which is the inverse phase of the Fourier transform. This is certainly the choice. Well, I mean, let me say that if you don't make this choice, you would be crazy not to make this choice. This is, of course, the best choice you could do in a smooth setting. Right? There is no reason not to choose. This is at your disposal, so why wouldn't you just choose the phase of the inverse Fourier transform? And of course, that's the choice which is done 100% of the time. Except that here, we run in a very funny problem, which is that due to the regularity, you are not allowed to make this choice. Okay, so let me try first to explain you why this choice, which is the one everybody would do, is actually is actually forbidden. Okay, so let me remind you what are the constraints you have on this choice, and that will allow us to understand why there is actually an issue here. So the first constraint, well, this one is certainly satisfied by this choice x dot omega. The first constraint is that you are asymptotic to x dot omega at infinity on your initial manifold, on your initial slice sigma naught. So this one is certainly satisfied by your choice. The other constraint that you have is that, remember, one of the very important estimates we have in space-time is the fact that the mean curvature is any infinity in space-time. But of course, since it's a transport equation, you can only transport what you had from the beginning. You know? Remember, maybe let me just remind you that there is this term here. You have a transport equation, so there is this term which needs to be in L infinity, which is the mean curvature at initial time. So I do need to have the mean curvature to be in L infinity at initial time. And finally, of course, well, this is not really a restriction, but of course, you know, as long as I'm able to make a choice, let's just make the best choice possible. Okay, so I have issues of regularity, so of course, the more regularity I get, the better. So let me try to make a choice that optimizes the regularity with respect to x on one hand and with respect to omega. Actually, we'll see that with respect to x, not really the issue, but it's rather omega that bothers me. Okay, so now let me explain you why the usual choice certainly has no chance to work. Okay, and that's related to the constraint here, which is written there. So the mean curvature, well, the mean curvature is always at the level of one derivative of the metric, right? If I write it, that's one derivative. That's one. The mean curvature, you could write it as one half. Now you can write it always. So if I'm talking about my. So remember, you have your level surface HU, you have your two surface PSU, and you know very well that so this is the normal here. It's parameterized by S. So it's Li T. You can always really L. Sorry, the normal is L. You can always write your second frontal form as Li L of your metric G. So if I call, let me call the induced metric. Let me call gamma to be the induced metric by G on PSU. Then you could always write the second frontal form as one half of the Lie derivative with respect to in the direction of the normal of the metric. Okay. So in particular, you see that the second frontal form is at the level of one derivative of the metric. It's not any derivative, but it's one derivative of the metric. So in particular, one derivative of the metric here. Remember, you are at the level, basically, as we said, you are at the level of metric in H2. Your metric is in H2. I mean, it's stated in a different way. We said that curvature in L2, but in essence, it's equivalent to metric in H2. So that means that so here your H2 on sigma naught, so basically your H2 in R3, you should think. So if I take a derivative of the metric, that means that the derivative of the metric is in H1 of R3, H1 of sigma naught, so H1 of R3. And as you know, H1 of R3, it does embed in L6, but it does certainly not embed in L infinity, right? I mean, actually, even in 2D, it would be wrong, but certainly in 3D, it's totally wrong, okay? So this embedding being totally wrong, that means that if you take a generic choice without paying attention at the geometry, you're dead simply because you have one derivative of the metric in L infinity, and this is not consistent with our assumptions. Okay, so this means that, in particular, if you do the usual choice x dot omega, this has no chance to work. There's no chance why this choice would be adapted to the geometry, okay? So in other words, we need to make a careful choice which allows you to have this constraint satisfied, okay? Okay, so now let me introduce some geometric objects. I mean, I'm going to introduce some objects which are very similar to what I did in space-time, but now I'd like to consider the foliation of sigma naught by u. Okay, I constructed the foliation of the space-time by u. Now I want to construct just the foliation of the initial slice sigma naught by u. Okay, so it's going to be objects which are very similar, but it's just, let me give a slightly different name so that we don't make any confusion. Okay. Okay, so let me, again, so now let me write the slice sigma naught like this so that you can see it, and let me, so I have a foliation of that sigma naught by my u, so these are u, this is u is equal to u1, u is equal to u2, u is equal to u3, okay, and I want to introduce, as usual, so these are, okay, so this is what is called pu1, sorry. So this is pu3, pu2, and this is pu1, okay? And so I call pu the level surfaces of u in sigma naught. So now because I'm in dimension 3, the level surfaces are two-dimensional, so these are two surfaces which are level surfaces of u, so that's called pu. I again introduce the lapse or the inverse foliation density, which measures the infinitesimal distance between the slices of my foliation. So sorry, in space-time I call it b, and here in space I call it a, but it's essentially the same thing. And then I'm introducing the normal to the foliation. Okay, so these are very similar to what was done, but now it's done in a fixed slice. So let me draw it like this. So you have sigma naught. And you foliate it. Yeah, doesn't matter. So let me foliate it like this. So you have pu, and then you have the normal to p, which is unit normal to p, which is n, and so remember your space like here. So n is just a space like vector. So I have g and n is equal to 1, in other words. And then again, a is the infinitesimal distance. So if I take another pu, I see that a measures the distance between my two slices of the foliation. Okay, and I'd like also to introduce the second frontal form, theta, of this foliation. So as usual, theta, so n is the unit normal, so you differentiate the unit normal along tangential derivatives, and that gives you the second frontal form. So as usual, it's a symmetric to tensor. Okay, so what is the situation in the flat case? It's interesting to remember what it is. So in that case, you have sigma 0 is R3. The metric on the initial slice is the Euclidean metric. You have the k, the second frontal form of sigma 0, which is 0. And again, of course, in that case, by the way, in that case, of course, the good choice is to take u is the x dot omega, and the planes are x dot omega is constant. So these are now the two surfaces are planes. As I said, the good value for the lapse in the regular foliation is 1, so a is equal to 1. N is constant equal to omega, and the second frontal form is 0 because you have planes. Okay. Okay. So in the flat case, so if sigma 0 is equal to R3, and if G0, the metric on sigma 0 is just the Euclidean metric, then it's clear that you just get planes. You get a foliation by planes which are orthogonal to omega, right? So you have foliation by planes which are orthogonal to the same vector omega. Okay, so that's the situation in a flat case. So these are the planes orthogonal to the same direction. Okay, so now I need to relate this. So here it's the second frontal form, but in space-time as as embedded in HU, which is the level hypersurface of U in space-time. And here, trace theta is the second frontal form of the level surfaces of U embedded in sigma t. Okay, so I need to relate them, right? You have two second frontal form. Here you have sigma 0, and here you have HU. You have the same surface which is embedded both in HU and in sigma 0. So of course, because it's the different normal in each of them, it's a different second frontal form. So I need to relate them. And they turn out to be related through the second frontal form of sigma 0. Okay, so it turns out that trace chi is equal, so the mean curvature in space-time as being embedded in HU is the mean curvature as being embedded in sigma 0 plus k and n. Okay, so let's forget about let me not talk about maximal pollution assumption. If you know, it's good. If you don't know, it doesn't matter. But anyway, this is how you relate the mean curvature, both mean curvatures. It's related through a second frontal form of the T foliation. Okay. So in other words, I could rephrase this because here is in space-time. I want to have everything expressed in terms of the initial slice. I could rephrase this as trace theta plus KNN is L infinity. Okay, so let me rewrite this. I want one of the main obstruction I have to construct in my foliation is this has to be in L infinity. And again, this is not consistent. This is not consistent with the regularity that you have. So you have to make a geometric choice which forces this condition in some sense. Okay, so I want to force this condition. So of course, what is the easiest way to force this condition? Well, I mean, I think there's something very natural here, which is, of course, the first thing you have to try is just set this to be 0. So here, okay, well, maybe I should first say the following thing. So here, I want to make a choice for U on sigma naught. What is a choice for U? I mean, you can actually see that the only freedom you have is precisely the mean curvature. I can choose my mean curvature. Once I have chosen my mean curvature, that totally sets the that totally freezes the foliation, if you want. Okay, so I want to make a choice for the mean curvature, and that will be my choice for U. So the easiest choice for the mean curvature is to say that the mean curvature, actually, you could say mean curvature is equal to minus k and n. Okay, so this is the choice I want to make. So first of all, let me mention, so if you make this choice again, it's a scalar, you're making a choice for a scalar function, so if you fix one condition, that that should fix the foliation. So indeed, that's what happened. That's what happens. If you fix the mean curvature, that fixes totally foliation. So this equation is very familiar, right? If you're familiar to Riemannian geometry, this equation is very well known. Prescribing the mean curvature, it's a prescribed mean curvature equation, right? In particular, if I'm in the flat case, k is 0, I'm prescribing mean curvature to be 0. That's the minimal surface equation in dimension 3. Okay. So it's a very familiar equation. It's certainly geometric. It certainly satisfies this. So there is all reasons to believe this is going to be the right candidate. And unfortunately, it is not. The reason for this is that it's very bad with respect to omega. With respect to x, there's usually no problem. This satisfies this, but it does not. It does totally. It is very bad with respect to omega derivative. So let me now explain why. Okay, so let me. So let me spend the rest of the talk on this slide. So the end of the talk on this slide. So I'd like to explain you why this choice, which a priori looks like the right one, is not correct. So for this, I'd like to. So again, you can derive structural equation by commuting. It's always the same. You look at the Hessian, you commute derivatives, and you relate it back to curvature. Okay. So here I can do the same and get a structural equation which relates the lapse of my foliation to the mean curvature. And here you have the second frontal form square. Okay, so here, so take my word that you can actually derive this equation where you relate the lapse to the mean curvature through curvature, because again, you have commutation of derivatives which is to a curvature term. So here, you see that you get the Ricci term. It's the Ricci at initial time, right? It's not the space-time Ricci, so this one is not 0. It's actually It's the curve. It's related to the curvature of the initial slice. It's the Ricci spacetime, which is 0, not the space Ricci, not the Ricci of the space-like surfaces. Okay, so here, what do you learn from that equation? So I claim that the basic quantity which is important is to control the lapse. That's the guy that's crucial here. And here, if you look at this, you see that whatever choice you make for trace theta, essentially you will pay the price that with respect to x, this is only in L2. So at best, you recover two derivatives of L2. So at best, at best you recover two derivatives for the lapse in L2. And because the lapse is at the level of one derivative, you get three derivatives of u in L2. And actually, this is not correct. If you look carefully, you get three derivatives in L2 in certain directions and not all of them. But certainly, anyway, whatever the choice you make, you will always pay this price. So it's certainly not for derivative with respect to x that the choice will matter. It's derivative with respect to omega. Okay? So now let's see why you pay with respect to omega. And this is a computation which is very similar to what we've seen when we commuted omega with the Ricci-Leray equation, with the transport equation for trace chi. You see that if you commute with omega, the price you pay is this commutator between the omega and the angular Laplacian. Okay, so sorry, maybe I should, sorry. So my notation is that, again, the angular derivative, that's the covariant derivative on PU. So it's the induced covariant derivative on PU, sorry. Okay, so induced covariant derivative with respect to PU. Okay, so now, of course, this is a Laplace-Beltrami on PU, and you commute the Laplace-Beltrami on PU, you get this commutator, and as usual, this commutator, because your foliation depends on omega, you pick up, this depends on omega, and you pick up actually one tangential and one normal derivative, which tells you that the price you're paying for omega is that you have to have some regularity with respect to normal derivative. If you don't have any regularity with respect to normal derivative, you will never be able to take omega derivatives, okay? And the interesting thing is, if you look at this equation there on the top, a priori, it only controls tangential derivatives, right? It does not control any normal derivatives. You just control the tangential Laplacian of A. Okay, so you're missing the control of normal derivatives if I look at this equation. And in particular, you see that if you use this choice here, which is prescribed mean curvature, you see that unfortunately prescribed mean curvature is not going to give you any further information for A, and you just get two angular derivatives of A, and therefore you cannot differentiate with respect to omega. So that's why this choice is wrong. So let me tell you what is the choice which is right. And actually it's interesting because this one is also very natural in geometry. So I want to, instead of prescribing mean curvature, now I want to say that mean curvature minus KNN is not 0, now it's 1 minus A. So 1 is just a normalizing factor, so don't forget about the 1, but it's the A that's interesting. So first of all, let me tell you that this equation is nothing but a variation of the mean curvature flow, right? That's the mean curvature. Why is it the mean curvature flow? This prescribes the speed of the foliation. So forget about the KNN. So if K is 0, if I'm in the flat case, K is 0, then, and forget about the normalization, it's not important. But this is nothing but, it's 1 of the gradient of U, so this is just the speed of the foliation. So I'm having a foliation, I'm starting with a slice, and I'm asking you, right? I'm starting with a, sorry. So I'm starting with, so I'm in sigma naught, and assume that I have a slice. So I'm starting with a slice PU naught. And I'd like to know how to advance, how my foliation has to advance. Well, it's very easy. If you look at this equation, what it tells you is this is the speed at which I'm going to advance in that direction. So I want to construct a new slice, and I just have to prescribe how is the speed that constructs my new slice of my foliation. And this tells you that the speed is proportional to mean curvature if K is 0. And the speed proportional to mean curvature is exactly the mean curvature flow, right? You advance, you take your initial surface and you advance it proportionally to the mean curvature. Okay, so this is just a variation of the mean curvature flow where now you had an additional term KNN and a normalizing factor because of our regular foliation, the lapse is 1, so I need my normalizing factor. Okay, so this I claim is better behaved because now you get also an extra bit of information, which is regularity in normal direction. Why? Because the trace theta here has an A, so you pick up a D and A, and if you put it on the right-hand side, you see a parabolic type equation, which you should expect because mean curvature is a parabolic flow. Okay? So you get parabolic flow, and in particular, therefore, for parabolic equation, you get extra information with respect to normal derivatives. Okay? And then, so let me finish with the kind of estimates that you get. So first of all, as from the start, you knew you would always control two angular derivatives. That was already given. But now you control one angular derivative because of parabolic flow. And furthermore, now it's not enough, but because of the structure of the equation, and in particular, the so-called constraint equation, which I did not mention, but which have to be satisfied by initial data, and the Bianchi identities, I can commute with normal derivative. And this guy, when I take normal derivative, is better than what you would think because of the structure equation. And you get an extra bit with respect to normal derivative. You even are able to go as far as 2 normal derivative. Okay, so this, in other words, the fact that you get normal derivatives is because of the parabolic fixture, but the fact that you get that much is because you also use the structure. Okay, and finally, let me mention that therefore this allows you, because you get normal derivatives, you can differentiate with respect to omega. And I'd like in particular to mention this estimate here, because this estimate I did use for the control of the parametrics. I said that you have one space derivative, one omega derivative of u in L infinity. So this is the estimate that is needed to control to get the Strickhardt estimates that I use for the Strickhardt estimates. Okay, well, so I'll finish here, and this afternoon I'll discuss how this control that I explained you about of the Conal equation allows you to control the parametrics.